Hello, my name is Daniel Rowe, and I'm going to present our paper titled Masked Wavelet Representation for Compact Neural Radiance Fields. The goal of this paper is to find a parameter-efficient representation for grid-based neural fields. To achieve this, we propose using wavelet coefficients for grid representation. Additionally, we utilize a trainable binary mask to prune out insignificant coefficients. By employing this method, we observed that more than 95% of the grid parameters can be discarded without significant visual degradation. Furthermore, our method can be applied to any grid-based neural fields that adopt grid structures other than MLP. Before delving into our work, I would like to start with the background of this paper. Neural radiance fields have demonstrated impressive performance in rendering 3D objects and scenes, while non-MLP data structures have been proposed to reduce the computational cost of neural fields. They come with increased storage requirements. Therefore, our aim was to address the following question: how can we maintain reduced computational cost while minimizing storage requirements? Paired with MLP and the volume rendering equation, neural radiance fields, in short, NeRF, generates high-quality images even from unseen view directions. However, due to the coordinate-wise dense computation, computational costs have been demanding. As an alternative, grid-based neural fields have been proposed to mitigate the training and inference costs compared to MLP-only neural fields. Nevertheless, adopting additional grids requires a significant number of additional parameters. To achieve efficient neural field representations, several studies have explored frequency-based parameterization. While these works have shown promise, they have not fully matched the performance of MLP-only neural fields. In addition to frequency-based neural representations, other network compression techniques such as pruning and quantization can also be applied to reduce the size of grids. This slide illustrates how typical grid-based neural fields such as TensorF work in an abstract sense. It demonstrates the process of extracting corresponding features through interpolation for each coordinate, followed by aggregating and processing these features to predict color and opacity values of each coordinate. In our approach, we introduce an additional process during the training phase, which is the inverse discrete wavelet transform. We optimize wavelet coefficients and, before rendering, we perform an inverse transform on the wavelet coefficients to obtain spatial grids. To prune out grid parameters, we propose using trainable binary masks. These masks are trained alongside the wavelet coefficients using the straight-through estimator technique, determining which coefficients should be discarded. Upon completion of the training process, we only encode or store the non-masked coefficients. As a result, trainable masks are no longer required. Importantly, this process incurs negligible cost during inference. Specifically, just before inference, we perform an inverse transform on the encoded wavelet coefficients to construct spatial grids. The subsequent rendering process, including grid sampling and interpolation, remains identical to that of spatial grid-based neural fields. Furthermore, since our method does not address grid sampling, feature aggregation, or the processing of extracted features, it can be applied to any grid-based neural fields. Then why the discrete wavelet transform? DWT is a widely used transformation method in signal processing and data compression. It can capture both frequency and local information. The left figure provides an example of wavelet coefficients, and the right figure illustrates that the DWT outperforms other representation schemes, such as spatial or discrete cosine transform. Additionally, higher-level wavelet transforms yield even better performance. To validate the effectiveness of our method, we conducted experiments on 4 different 3D object datasets, commonly used in the neural fields literature. As indicated in the graphs, applying our method improved distortion curves across all datasets. We can control the size and quality by adjusting the loss weight on the trainable binary mask using lambda m. On the right side, we can observe the green and brown curves. The green curves represent the distortion curves when applied to relatively smaller grids, while the brown curves represent those applied to comparatively larger grids. As demonstrated by these curves, applying our method to larger grids maximizes the benefit. These images illustrate the qualitative results of our method. The left images of each object are the rendered results after discarding more than 97% of the total coefficients. Remarkably, we achieved such high sparsity without discernible visual differences compared to non-pruned baseline. To summarize, we proposed a compact representation for grid-based neural fields. Our approach introduces a novel masking strategy along with the utilization of multi-level wavelet transform on grid coefficients. Under memory constraints, our method achieves state-of-the-art performance and can be applied to any grid-based neural fields. This concludes my presentation of the paper. For more detailed information, please refer to our paper. If you have any further questions, feel free to reach out. Thank you.